All right, so let's do this question. It says, or it's asking, what is the focal length of a magnifying glass that produces a magnification of 3.5 when held 6 centimeters from an object, such as a rare coin? Um, hmm. There's a bit of an ambiguity here, I think, because this combination of two things, magnifying glass, which might make you think, oh, so this is about simple magnifier. But if it's a simple magnifier, you will find that the angular magnification formula, when you look it up from textbook, you will have two formulas. The angular magnification capital M is either the near point divided by focal length, if you are looking at it with relaxed eyes, or it's this plus one if you are using strained eyes condition. Now, I have a reason to think this reference to magnification, it's actually linear magnification. As in what we've been dealing with, the linear magnification defined as the image height over image object height is equal to minus the image distance divided by DO. This is the definition. This is a derivation that was done geometrically in lecture. I think it's referring to linear magnification mainly based on the fact that it's talking about, how far away it's held from an object. In the case of angular magnification of a simple magnifier, how far away it's from an object, it's actually kind of specified in how you use it. You have to imagine holding that magnifying glass right in front of your eye and then just looking at the object as close as you can. You'll be doing that in lab, by the way. So if it's a very unusual way of doing it, but because that's if they meant by magnification 3.5 angular magnification, it kind of doesn't make sense to me that this distance is specified. So I'm gonna assume that it's a linear magnification, work this through, and then somehow if it tells me my answer is wrong, then I'll go back and try to make a sense of angular magnification somehow. So, with the assumption that they are talking about the linear magnification, then it's a quite standard setup of a converging lens. We don't know the focal length. And it's a magnifying glass, and you're probably looking through it still. So I believe, do you need a let's see if it matters if you are dealing with a virtual image or real image. So I'm going to assume it's a virtual image because that's how you use magnifying glass usually. You don't use it to project a real image. So my object then should be inside the focal length somewhere here. And I think we were given the object distance, DO. And you do the ray tracing, and the ray tracing will produce diverging rays on the outgoing side. They will appear to converge on the opposite to the outgoing side, which with our image. So there will be some image distance here. Okay, and I have the focal length here, and the relationship between the focal length, image distance, and object distance, it's given by the thin lens formula. 1 over DO plus 1 over DI is equal to 1 over F. Let me be systematic and treat it like the kind of general physics problem solving, which is you first focus on getting as many equations as unknowns. So this is my first equation. Let's see how many unknowns we have. So we know DO, that's 6 centimeters. Good. So we don't know DI, you don't know F. We got 2 unknowns. So, which means one equation is enough. I need a second equation, and that'll end up being coming from this here because I recognize we are given magnification. So let me write down the second equation. So magnification is equal to the HI over HO isn't relating it to anything that we know, but if we say minus DI over DO, these are already variables in the other equation. So even though DI is still unknown, I'm not introducing any new unknowns. Magnification was given. So we have 2 unknowns, 2 equations, out to be solvable. So this is the very kind of first stage of any physics problem solving. You make sure you have same number of equations. This is really how much information you have represented as equation as same number of unknowns. It's a kind of general. I hope this was taught to you in like college algebra. If you have a linear or some system of equations, usually you need the same number of equations as unknowns to be able to solve it. There's like they have to be independent equation. There's some nuances there, but hopefully you feel like you know that. Let me go through so once you've done that, then the rest is math. And this rest is math. You could do it using Sage Math. And I feel like I might not have done as much Sage Math demo in this class, so let me do that. I'm going to use Sage Math. So this part can totally be automated. Once you have equations, then all you have to do is type it in here, type in some commands that'll have Sage Math calculate what the answer is. So let me do that. I need to declare some variables. By the way, if you don't know how to use something like a Sage Math, I recommend that you ask ChatGPT. ChatGPT is really good with helping you with the programming questions. There are some like programming tasks that I know no JavaScript, but I've been able to create some very simple JavaScript code with the help of ChatGPT. I still don't know JavaScript. Variables. Equation 1 is 1 over dO plus 1 over di is equal to, this is different, has a different meaning from this. This is assignment symbol. It's equal to 1 over f. Equation 2 is assigned as m is equal to minus di divided by dO. Let me to make sure I've typed in equations 1 and 2 correctly. Just make sure it doesn't complain. Yeah, those are my equations 1 and 2. And there's a syntax called command called solve. It's the equation solver. It solves for a system of equations. So this is equation 1 and 2 enclosed into what's called a tuple. You can also use a list. That's my system of equations. And I tell Sage Math to solve it for my two unknowns, di and f. And it looks like I'm looking for f, so I'll put f first. Then the first equation it gives me will be for f, and then di. Yeah, and then Sage Math will treat everything else as a known quantity. I click evaluate, then it should, yeah, that's my system of solutions, f and then di. So I'm just gonna go into this particular expression. That's kind of two levels inside the list. So I get to the first element of the outer list. And then again, first element of the list inside that should give me that equation. In fact, let's just do that. That's the equation. And I could just type in the numbers into a calculator and do the calculation that way. Another thing I can do is I can use something called a substitution syntax. It's a way to automate all the number plugging in. So I say object distance is equal to 6 centimeter. Magnification is equal to, and here I think a positive makes sense if, yeah, if they actually did mean a positive magnification, then it will definitely mean virtual image. So yeah, I'll just put in plus 3.5 for n. I think that's it. So now Sage Math doesn't do units, unlike Wolfram Alpha. So you do want to double check if I specify dO in centimeter, m is unitless. So the right hand side will just be in centimeters. So I'll get focal length in centimeter. So you do have to work out the units yourself, because Sage Math won't do units for you. So I get a number of 8.4, and that ought to be in centimeters. So 8.4 centimeters. Yeah, and it says it's correct. So my interpretation that this is talking about linear magnification must have been correct. Oh, and just for like trivia. So if it was producing a real image, then your magnification would have been negative. So if you do minus 3.5, I'm sure it'll still work. Yeah, and the this shorter focal length lens with the same setup will produce a real image that's like 3.5 times as far away as 6. So that's this question. It's a fairly standard, like a single lens equation. I wouldn't say it's easy, but once you recognize the setup and realize what you need to write down, then I think it's not overly tricky. Really, the hardest part is where it says magnification. That, frankly, is a little bit ambiguous. So it does, especially in the context of magnifying glass. But if you thought it was angular magnification, then you would have tried some things and then realized that it doesn't work, and hopefully not to try linear magnification instead of angular magnification. So.